So in this part of the video, we're gonna focus on the consumer, and we're gonna talk about consumer surplus. So I have the consumer demand curve up here, and we have number of donuts on the x-axis, price per donut on the y-axis. And I've marked on here the equilibrium point that we found in the last part of the video, where if the price is set at 80 cents per donut, then the consumer will purchase 3 donuts. What I do not have drawn up here, and we don't need it for this part, is that supply curve, which also goes through this point 3, 0.8. Okay, so again, we are focusing on the consumer's perspective for this part of our video. Okay. Now, what I have written down over here is that the area under the consumer demand curve between x equals 0 and x equals 3 describes the amount of money the consumer is willing to spend to purchase 3 donuts. So let's shade that region. Here we have our consumer demand curve. It's called a curve even though it's a straight line, that's okay. But we have this consumer demand curve. Here's x equals 3, here is x equals 0, and the shaded region under our graph and above the x-axis is this region right here. And in terms of a label on this region, our y-axis is dollars per donut, and our x-axis is number of donuts. So when I write this down, the donuts cancel, and we're left with dollars. So it kind of makes sense that this area should represent a dollar amount. Thank you for holding that for me. And so what we want to do is we want to calculate this area. And there's a couple of ways to do this. If you've taken an econ class and you've talked about consumer and producer surplus, you may have evaluated some of these areas and you may have used some geometry. For example, this shape right here is a trapezoid, and there's formulas for evaluating the areas of trapezoids. But we're going to talk about it in terms of calculus because it's not always the case that your consumer demand curve is a diagonal line. Sometimes it's curved, like our supply curve is curved. Okay? All right, so to evaluate this area, let's see, that makes me think of a definite integral. All right, so to find this area, the amount of money that the consumer is willing to spend to buy 3 donuts, we are going to be evaluating the definite integral from 0 to 3 of 1.4 minus 0.2x. All right, and then we have a dx at the end because that tells me we're at the end of the function. Okay, so to evaluate this definite integral, I'm first going to look at the indefinite integral of 1.4 minus 0.2x dx. And I'm going to find the antiderivative. So the antiderivative of 1.4 is 1.4x. And the antiderivative of 0.2x, well, let's see, I'm going to add 1 to the power and divide the number in front by that new power. And then I have a plus c. Okay, so I'm going to clean this up a little bit. Then I have 1.4x minus 0.1x squared plus c, and everything except for the plus c will be my capital F. So I found my antiderivative. Now I'm going to plug in the top number and the bottom number and subtract. So capital F of our top number, let's see, I think we need some more shredded napkins to hold on to. That's very important. Here you go. Capital F of 3 will be 1.4 times 3 minus 0.1 times 3 squared. And I checked that ahead of time and I got a value of 3.3, but you should check that as well. Then I'm going to plug in 0. So capital F of 0 will be 1.4 times 0 minus 0.1 times 0 squared. All of that's going to be equal to 0. Okay, so once I have found my antiderivative, plugged in the top number, plugged in the bottom number, now I subtract capital F of 3 minus capital F of 0. And we have 3.3 minus 0, which is 3.3. So our definite integral is equal to 3.3. Okay, so what is that number telling us? Well, that 3.3 is the area of this shaded region over here. And what that tells us is that our consumer is willing to spend up to $3.30 for 3 donuts. Okay. Now, so the customer goes up to the table and says, okay, here's the $3.30. And the cashier says, okay, well, the donuts are 80 cents a piece. So the price that the customer is really paying is 80 cents times 3 donuts. So let's write that part down. The customer is actually spending $0.80 per donut times 3 donuts, which is $2.40. So the customer is willing to spend $3.30. They really only spend $2.40. So the customer feels like he or she is coming away with a surplus of, well, let's see, it was $3.30 is what they were willing to pay, but they actually paid $2.40. So the customer is coming away feeling like he or she has a surplus of 90 cents. And we call this number our consumer surplus. Okay, so the idea of consumer surplus works anytime that you have a consumer demand curve. So kind of as a summary of the donut example, whenever you have an x-axis that represents number of units and a y-axis which represents price per unit, and your consumer demand curve which relates the price per unit to the number of units that the consumer is willing to purchase, then we can talk about consumer surplus. So let's say that we know what our equilibrium point is. And that equilibrium point we get if you imagine the supply curve kind of coming through here as well. That equilibrium point has an x value that we'll call x subscript e for equilibrium. And then the y value is our equilibrium price, so we call that p subscript e. And what we saw with the donut problem is that the entire area under the curve, this entire trapezoidal area, this area represents the amount of money that the consumer is willing to spend to purchase, in our case, 3 donuts, but in general, x sub e units. So we have the money that the consumer is willing to spend, and we calculated that value as the integral, and we had our consumer demand function in the middle, and we evaluate that integral starting at 0, always starting at 0, and ending at whatever number of units we're talking about, which for us is always going to be the equilibrium quantity. So from 0 up to x subscript e. For us, that was 3 donuts. So from 0 to 3 donuts. Okay. And then we said, all right, how much did the consumer actually spend? And the consumer actually spent that amount for us was the price per unit times the number of units. So in our case, that would be the equilibrium price times the equilibrium quantity. And we subtracted that amount from the amount that they were willing to spend, And what that did is that gives us our consumer surplus. In terms of our picture over here, that first integral, that is the total amount that they're willing to spend, is this entire trapezoid. And the amount that the consumer actually spends is this rectangle here that has a height of the equilibrium price and a width, which is the equilibrium quantity. So this big X right here is the amount that the consumer is willing to, or the amount that the consumer actually spends. So if the whole thing is how much they're willing to spend, and the X is how much they actually spend, then the remaining portion, the portion that's left over, is this triangular region up here. And this triangular region, the portion below our demand curve but above this rectangle, that amount, that is our consumer surplus. And that area represents the amount of money that the consumer feels they have saved by spending this much after they were willing to spend this much. Okay, thanks.